Hello, today we are going to take a look at Charles' law. So yesterday was, or day before was Boyle's law, and we learned that pressure and volume are inversely proportional. Today we're going to keep the moles and pressure constant and only talk about changing the two variables of volume and temperature. And Charles' law says that the volume of a gas is directly proportional to the Kelvin temperature. That means all temperatures must be in Kelvin to work these problems. When you graph a direct proportion, it does graph linearly. And so this is basically how you get the slope of a line. And that's how come that is the formula, V1 all over T1 equal V2 all over T2. And so along the x-axis, we have temperature. Along the y-axis, we have volume. So here's at 100 Kelvin. You can see you have 200 milliliters of volume. When I double that Kelvin temperature, look what happens to the volume. It doubles also. So that's what it means to be a direct proportion. If you double one variable, the other variable will double also. If you half one variable, the other variable will be 1/2. So on and so forth. Charles balloon are basically how hot air balloons work. You heat up the air inside the balloon, it becomes less dense, and so there's it fills up the balloon, and you float in air, even though you just contain air, but your air is much lighter because it's much warmer. Charles' law is V1 all over T1 equal V2 all over T2. I've already kind of started this problem. We have a balloon inflated in a room at 24 degrees Celsius and has a volume of 4 liters. So those would be my ones. Notice I've already changed my Celsius to Kelvin by adding 273. So I took 24 plus 273 to get the 297. I took the 58 degrees Celsius, added 273 to get the 331. So I want to know the new volume here. So I have got 4 liters all over 297 Kelvin, because those were the ones, and that's equal to X all over 331. So again, when you set up a direct proportion, liters and liters go on top, Kelvin and Kelvin go on bottom. And so to solve this, you are cross-multiplying, and then you divide these. So you multiply the extremes and divide by the mean here. So you get 4 times 331 divided by 297, and that gives me 4.45 liters, because I have 4.546. Sorry about that. I didn't round correctly. I have 3 sigs working in the problem. Again, sigs with the addition, this might have 2 sigs, but because I'm adding it, this is to the ones place. So now my temperature that I'm using in the problem has 3 significant figures. So that's how the sigs work on that problem. The next problem, you have 6.8 liters with 325 Celsius. I'm going to add 273 to the 325, and I multiplied. So let me start over here. And I get 598 K. And 25 degrees Celsius is 298 K. So what I'm going to have here is I'm going to have 6.80 all over 598. And you can see that basically what's happened to the Kelvin temperature, this is almost 600, this is almost 300, so it's about halving. So I'm going to predict that my new volume will be about half. So to solve this, I take 6.80 times 298 and divide it by 598. And I get 3.39. And sure enough, that's just about half. And then the last problem, you have 5 liters of air at negative 50. That's going to give me 223 degrees Celsius. You'll never have negative numbers working in Kelvin. And so that's why it's used. And 373 Kelvin here. So I have 5 liters at 223 Kelvin I want to know what the new volume is at 373 Kelvin. So I'm going to take 5 times 373 and divide it by 223. Got 3 SIGs working in this problem, so I have 8.36 liters as my final answer. All right, you're ready to go in and take the quiz.